Hello everyone, and welcome to a new episode of Advent of Code 2016. As you can see, days 11 and 12 are both open to us, but I'm doing these in order. So 11 it is, unless some kind of drastic nightmare happens. I heard 11 is hard, but I don't know any details about it. I don't imagine it's going to be so hard that I give up on it and go on to 12, although there was one like that last year. I think day 14, I really disliked part 2 of that one. I still feel like it was a bad puzzle. The answer that turned out to be right was one that I feel like depended on unstated properties of the input, and that attempting to do things the correct way instead of the easy way led you into running out of memory, basically. Whereas doing things the easy way that's not guaranteed to work happens to work. And so I just was not very happy with that. Anyway, day 11, radioisotope thermoelectric generators. You come upon a column of 4 floors that have been entirely sealed off from the rest of the building, except for a small dedicated lobby. There are some radiation warnings and a big sign which reads, Radioisotope Testing Facility. Well, okay. According to the project status board, this facility is currently being used to experiment with radioisotope thermoelectric generators, simply generators, that are designed to be paired with specially constructed microchips. Basically, an RTG is a highly radioactive rock that generates electricity through heat. The experimental RTGs, geez, this is a lot of detail of what seems like just flavor, have poor radiation containment, so they're dangerously radioactive. The chips are prototypes and don't have normal radiation shielding, but they do have the ability to generate an electromagnetic radiation shield when powered. Unfortunately, they can only be powered by their corresponding RTG. An RTG powering a microchip is still dangerous to other microchips. Okay. In other words, if a chip is ever left in the same area as another RTG, and it's not connected to its own RTG, the chip will be fried. Therefore, it is assumed that you'll follow procedure and keep chips connected to their corresponding RTG when they're in the same room, and away from other RTGs otherwise. This is long! These microchips sound very interesting and useful to your current activities, and you'd like to try and retrieve them. The 4th floor of the facility has an assembling machine which can make a self-contained shielded computer for you to take with you, if you can bring it all of the RTGs and microchips. Okay. Within the radiation-shielded part of the facility, in which it's safe to have these pre-assembly RTGs, okay, there's an elevator that can move between the 4 floors. Its capacity rating means it can carry at most yourself and 2 RTGs or microchips in any combination. This sounds a lot like the farmer crossing the river with the goat and shoot, what are the other 2 things? Like a tiger or something? An alligator? And lettuce or something? Like the goat will eat the lettuce and the alligator will eat the goat? Something like that? I don't know. They're rigged some heavy diagnostic equipment. The assembling machine will detach it for you. As a security measure, the elevator will only function if it contains at least 1 RTG or microchip. The elevator always stops on each floor to recharge, and this takes long enough that the items within it and the items on that floor can irradiate each other. You can prevent this if a microchip and its generator end up on the same floor in this way, as they can be connected while the elevator is recharging. Jeepers. You make some notes of the locations of each component of interest, which is your puzzle input. Before you don a hazmat suit and start moving things around, you'd like to have an idea of what you need to do. When you enter the containment area, you and the elevator will start on the 1st floor. Okay. Wow. Holy cow. How big is our puzzle input here? Okay, so we've got a bunch of things surrounded by ands. Separated by ands and commas. Okay. Alright, so basically, there's generators described by a name of a metal or something, and microchips described as being compatible with that kind of metal. Huh. Interesting. This is a much smaller input than we have gotten on previous things. So this makes me believe that it's not, although it looks like something you could maybe figure out by hand. So let's see. The problem is the microchips, if they're in rooms without their own generator, but with a different generator. Okay. So like the first floor has a generator paired with its microchip and two other generators. The second floor has the microchips for those generators. Okay. And the third floor contains two generators and their microchips, and the fourth floor has nothing. So this is, in fact, such a small puzzle that I'm actually not going to write a parser for this. I'm just going to parse it by hand and input that in a more suitable form for my program, because this is like not a fun thing to parse. So how do we solve this problem? The thing that occurs to me as the most obvious is as a search over some state space, right? And you could try to do it in a number of ways. Like, what search algorithm you use, I think, is the interesting part. It's not too complicated to, given a state, determine what all of the legal moves from that state are. Basically, if you're on a floor with a generator or a microchip, whatever floor you're on, you can move one or two objects up or downstairs, basically, right? But you're further constrained that you can't ever take a microchip to a floor with a different generator unless its own generator is also on that floor. So, what is the actual question? The minimum number of steps. So, in order to solve minimum problems, you can sort of do, like, the most naive brute force thing is to do a breadth first search through the state space, right? And this may be a small enough... Right, our branching factor is, like, not that high, although I don't know, maybe it is. And our total number of steps is not that high, although I don't know, maybe it is. So it seems like we might want to do something a bit smarter than breadth first search. And A star is kind of the standout for this kind of thing, right? We can pretty comfortably figure out a heuristic for how far away we are from a solution. And given such a thing, A star is not that hard to implement. Like, I think I could probably do it without looking it up, but I'm not going to. I'm going to go look it up. In fact, actually, let's see if one already exists in Python that we can just use. You guys don't need to see my bookmarks. They're not very exciting. So let's see. Python search A star algorithm library. Algorithms 101. So there's a Python package named algorithms, apparently. So let's see. Can I just Python import algorithms? No. So I will probably have to install it. Okay. So what is included in here? How do I look at the documentation for this? Package index is where we are. If you want to use it, super sweet documentation. From algorithms, where are they though? Table of contents, algorithms, searching. Binary search, BMH search, depth first, KMP. What is KMP? KMP search on a string. This is all string search. What the hell, Python? You implement depth first search for me? And that's like the easy one. I don't need help with that. I need help with A star. Alright, well, I guess we're probably going to do it ourselves then, huh? Alright, how about this? 20 Python libraries you can't live without. How clickbaity. Hang on, are you guys looking at this now? You're not. Okay, now you are, sorry. We saw a library that was no good. 20 Python libraries you can't live without. Hey, this is all not stuff I care about, I don't think. This one is listed twice! No, Scrapey and Scapey are different things. Alright. Is there like a search thing or what? Highwinds, Scapey, Python, GUI, a million GUI libraries. Pygame, you could imagine, might have it. I mean, it would be. Oh my gosh! What a web page! Yikes! What year is it? Documentation? I don't know. Maybe I should just implement A star at this point. Yeah, this is not looking very promising either. All right. Well, algorithm A star wiki. A star search algorithm. Now it's going to remind me to donate. I actually already have, but I did it through work, and so they don't know it was me, and they keep bothering me. Okay, A star. Yeah. So it's basically like a heuristic-based breadth first, where you don't. It's. Is A star that good actually if you don't have costs? I guess it is, yeah, because it biases towards things that seem to be getting you closer to the output. Okay. A star for the one that incurs the smallest cost. And among these, yeah. Tree of paths determines which of the paths it's currently thinking about to expand into more longer paths. And it does so based on the total cost. It does so based on which one is closest, based on its heuristic, to the goal. And yeah, priority queue is like the normal thing, although a sorted map would also be fine, or a sorted set or something. Well, it'd be a little hard actually if you want to sort by like something else. I think what I implemented last year was A star in Haskell. I'm not sure. It might have been something else, but I think it was A star. Maybe it was breadth first. Who knows? The set of nodes already evaluated. Set of currently discovered nodes. Okay. For each node, the cost of getting from the start to that node. Jeez. These pseudocode is so weird to read because they choose like, I don't know. They choose something that doesn't really look, it just doesn't make a lot of sense. Like map with default value of infinity. Okay, whatever. Anyway. For each node, the total cost of getting from the start to the goal. All right, this is not a useful description of the algorithm for me. I've seen it described quite simply, and I'm not sure where. Maybe Dijkstra's algorithm is better. What's Dijkstra's algorithm all about? It's not very interesting to us because it's so if each edge in the graph has the same cost, then Dijkstra's algorithm is basically just a breadth-first search because it doesn't have a heuristic for how far you are from the goal. Basically, it figures out like, oh, what's the shortest path I've so far traveled on? Let's see if maybe the goal is over there, and then expands that node. But that sort of is basically just the same as breadth-first search when all of the paths are length 1. Whereas A star has this heuristic that lets you avoid doing moves that seem to be counterproductive. Well, where can I find a good description of A star? Let's try this. I hope you guys enjoy reading Wikipedia with me. This page is in German. I agree, actually. What? How did that happen? Usually when I get those pop-ups, it's like completely... Oh no, it just isn't written? Huh. What's with this German page? I guess it's just a translation of the same one? I don't know. We don't need these Python things. So, my recollection of how A star works is that you keep a list, or well, some data structure of all the nodes you've traveled to so far, sorted by the sum of how much work it took you to get there, and the heuristic of how far you are away from the end. And then at each step, you find the one where that sum is the smallest, and you expand it into all of its other nodes. Right? Can this ever cause you to revisit a node in a way that is better? No, because you should, I believe, always get to a given node in the fastest way. That's the point. That's why it's a good search algorithm, I think. Pathfinding. So A star assigns a weight to each node equal to the weight of the edge to that node, plus the approximate distance between the node and the finish. Approximate distance is found by the heuristic and represents a minimum possible distance. So we could make variously good heuristics, but let's see. Okay, minimum. The important thing is that your heuristic should never underestimate how. Sorry, this is a minimum. It should never overestimate how long it will take to get to the exit. As long as your heuristic only ever underestimates, you'll get the correct solution. It's just the better your heuristic, the faster you will find it. A star heuristic uses this to improve. When the heuristic evaluates to 0, A star is equivalent to Dijkstra's algorithm. And as the heuristic estimate increases and gets closer to the true distance, A star finds the optimal path. When the value is exactly correct, A star examines the fewest nodes. As the value increases, A star... Oh, if it gets higher than the correct value, A star no longer guarantees the best path. Which could be fine in some applications, as they point out, but not for us, since we are being asked what the length of the minimum path is. Okay. The minimum number of steps. Each elevator stop counts as one step, even if nothing is added or removed. Okay. Well. Should be interesting. So let's actually remove the input file. We're not going to use it. And get started, I guess. Oh, I forgot to leave day 10. Here we are, day 11. So we have to always, let's see, our heuristic must never underestimate how long it will take to get somewhere. Is that right? Yes. It's okay to overestimate. Wait, no. Because if heuristic is 0, then we have Dijkstra's algorithm. Okay. So we must never overestimate how long it will take to get somewhere. Okay, so it's a little bit tricky to even think about, like, about how to even, what even is our heuristic, really? Well, maybe let's worry about that later. And maybe it'll turn out that just doing a breadth first search, where we basically let our heuristic be 0, and then that'll be fine, right? And then we can work on a better heuristic later. So let's start modeling some stuff, right? Oops. I want to look at the, oh, we don't have the input in a file, right? I decided to keep it here. So let's paste it in and comment it out, and then we'll figure out how to model it later. So how do we represent a room? Is that how we want to start modeling things? We could have, for each room, a list of the objects in the room, or we could have a map where, like, for each object, what room it's in. That doesn't seem as useful as having a list of objects for each room. So maybe what we do is we have a list of rooms, 0 through 3, and we must never overestimate how long it'll take to get there. Yeah, I guess that means that our heuristic will basically just involve taking things upstairs and hoping for the best. It's okay if we underestimate by, like, backing ourselves into a corner and having to turn around. Okay. So for each room, a list of the microchips and generators in it. Maybe for each room, 2 sets. One set for microchip and one set for generator, right? That seems okay. All right, so let's say class room pass. Nothing interesting. Actually, there is something interesting we can do. Def illegal takes a self, and it's going to determine whether there is a microchip in this room that would get fried. We basically say for chip in chips, if in self.chips, if or actually not chip, for metal in self.chips if let's see, I guess we can be a little bit more, we can say if self dot what are they called? R somethings? TNGs maybe? Thorium nucleogenerators or something? RTGs. If self.rtgs is empty, no, they don't have that. They have if len of self.rtgs equals 0. Actually, empty set of this as a bool, please, is false. Okay, so if not self.rtgs, we can just do this. Return false. Actually, let's just call the method legal, and we'll return true. So it's always legal to have no to have anything at all in a room if there are no RTGs. Otherwise, for each metal in all of the chips on this floor, if not metal, I don't know, is there a not in? I don't know. If not metal in self.rtgs, return false, and then we'll just return true. Right? So a room is legal if there are no RTGs in it, or if I each chip in it has a matching RTG. It seems like we could also do something a little bit silly here. We could try returning forget it. I was thinking we could do a list comprehension and then return it and sort of let it get implicitly converted to bool or something, but it's just kind of a hassle, so let's not. So this is how we decide if a room is legal. It's a little bit hard to do backtracking search when you're dealing with mutation, right? Because we have to be able to see what nodes are available from this, but not actually modify the existing nodes. Now, in a language where things are not mutable by default, that's easy. But here, like, sort of the obvious way to do it would be to, like, I don't know. So we kind of need to let's write some add and remove functions for this. How exactly do we write that? I want a method on a room that I can pass to say, what are all the valid things I could remove from this room? And it'll give me a list of them. Yeah, I guess. How exactly is the normal way to do this in Python? It's pretty easy in Clojure to just like get a copy of this room but with less stuff in it. And in Python it seems hard. Okay, let's see, like Python clone set. How to clone or copy a set in Python. You can just call set on it, of course. Or you can call .copy. All right. Well, that's not too bad. It's kind of a pain that we're going to have to do that for both sets and then construct a new room object. What if it returned... Yikes. This is nasty. There's a lot of detail work to do here. So what I was thinking is, what if it returned a pair of the stuff to remove, or rather, a list of pairs, each pair being some objects you could remove and what the room would look like after that, right? Is that good? It's kind of awkward. I don't know. It might be easier to just have it say, here's the things you could return, and then like give this also a remove method. Because we're kind of going to have to give it an add method also. Say, give me a copy of this room with some more things in it. How do you even get like a list of... It's kind of hard because I've put these things into two different sets, right? Maybe it would be easier if this was just a single set containing... Yeah, but then you have to iterate over the whole set. That's fine, I guess. Now let's see. It did say, I think, that you cannot operate the elevator with if it's empty, right? There's an elevator, yourself, and at most two things, and it only functions if it contains at least one thing. Okay, so we can't ever just go along the elevator ourselves. Give me back Emacs. Where is it? There it is. Is it easier to have two sets or one? I'm not sure. In the sense of checking for if a room is legal, it's much easier to have two sets. But in deciding what are legal ways to remove something from the room, it's easier to have just one. You know, I think it's probably correct to have just one set of both things, because that's sort of like how it is in like the real world, right? We have just this room has some objects, and some of them are one kind of object, some are another. The room is not divided in two with one thing on each side. And I think it's probably going to simplify things to just be able to pass around an object which is either an RTG or a yeah. I think actually that's a good idea. So I think we want actually a class for each of these two things. Class RTG. And we'll define broken for it, which is just going to return false. It's always legal to have an RTG wherever we want. But a class chip has a def broken self room and it's going to iterate over the objects in the room. And if it finds one that is its own matching type, if it's its own matching RTG, it'll return false. And otherwise, if it finds one that is a different RTG, it'll return true. Sure, that seems all right. So breaking equals false, and then for obj in room, is that a thing I want to do? I guess it's okay. If let's see. I'm thinking like I might want an RTG to declare what kinds of chips it breaks, and then the chip can just ask, "Do you break me?" Yeah, maybe that's fine. Yeah, okay, so let's try something like this. Def interact self metal if metal equals self.metal return fix, else, well, we don't need the else, right? Return break. And in here, we will write another interact here, def interact self metal to just do nothing. That's a little bit awkward, isn't it? We kind of have this three-state value, don't we? Of like, it's broken, it's definitely not broken, and it might be broken. Or rather, try to break it if there's nothing that saves it. Save it, or don't do anything to it. I was thinking of like having this thing just return like neutral. Let's just do that, neutral. And we need then another function that combines these things in a reasonable way. Def combine interactions AB if A equals fix or B equals fix, return fix. Otherwise, if A equals break or B equals break, return break, and otherwise we'll return neutral. So the idea is that at each step in this chip thing, we'll basically write breaking equals neutral, obj.interact, or breaking equals obj.interact of what does interact take? Self.metal. And then we'll return breaking equals break. So this seems okay. The chip iterates over all the objects in the room and touches each of them. And if one of them is an RTG that breaks it, it tries to break. If one of them is an RTG that fixes it, it puts it into the fixed state. And at the end, we check whether we were in the break state. Seems all right. I think we're going to want an init on both of these. Does init take a self? It does, right? Everything takes a self. And a metal. Self.metal equals metal. And we'll do the same up here. Okay. Boy, this code is getting a bit long, but that's all right. Did I actually call this correctly? Breaking equals, no, not this. Combine interactions of breaking and this. Yes, great. That looks better. All right. Well, there's a lot that we haven't modeled yet. Specifically, well, we haven't done like anything, right? It just feels like there's a lot left to do. We need a room to be able to tell us what the legal moves from a position are. Maybe that's not even a room's job, but we do need a way to build new rooms that are slightly modified versions of old rooms. So maybe what we'll do is def init of self and objects to be self dot objs equals do I want to copy objects here? It probably will already have been copied for me. And we can just remove, well, actually, for obj in objs, if obj dot broken, return true. Otherwise, we can return false. Oh, we're saying if it's legal. No. Yes. All right. I know how to type. And then we kind of want a def add takes self and objects, and it's going to return what is 1, 2 plus 5. Okay, so that makes a new copy. That's not too bad. Makes a new copy of the list. Yeah, and okay, that's fine. So let us then return room of self.ob. Actually, wait. How do you add Python add? Oh wait, we just did that. Self.objs plus objs. What happens if you add to a set? So 1, 2, 3 plus 4, 3. No such thing. Gross. Well, actually, we're not even really using it as a set, are we? We're using it as a list. So we'll just save it as a list and not worry about it. Okay. That's fine. How do you remove from a list? 1, 2, minus 2? No. Python remove from, or actually I guess what I want is Python list difference. Compute a list difference. Take two sets and subtract them. Yeah, make them into sets, subtract them, and convert back to a list. All right. Def remove self objects. Yeah, that seems all right. Return a new room of list of self dot, no, wait. List of set of self dot objects minus set of objects. Okay. So we're getting close to having the problem in a state, to having modeled the domain well enough that we can start working on the problem, I guess is what I would say. How do you find Python list combinations? How to get possible combinations of a list elements? itertools.combinations. Okay, that's not too bad. Yeah, itertools.combinations is just fine. Import itertools. So let's define def possible removals of self. It's going to return a list of lists of all the ways you could remove one or two items from the list, from the room. So basically it's return x for x in objects plus list of itertools.combinations of objects 2. Right? Seems okay. Does this compile? We haven't checked in a while. Incredibly, it all compiles. Great. So let's test removals. That's something I'm not so sure about. Room of 1, 2, 3, 4 dot possible removals. No, self.objects. Wouldn't be a proper Python episode if I didn't forget that. Yeah, you can remove 1 or 2 or 3 or 4, or 1 and 2, or 1 and 3, or 1 and 4, or 2 and 3, or 2 and 4, or 3 and 4. Okay, that's cool. So what if I were to remove, let's say not def r equals this, r dot remove of possible, r dot possible removals 0. It returns a room instance, of course. So what if we called vars on this? Objects 2, 3, and 4. All right. How about like the 5th item in the list? Objects 2 and 4. So it looks like remove is looking pretty good. And add is probably fine as well, although we might want to check it at some point. And so at this point, we're close to being able to turn this into a graph search. But I think now's a good time for a break. We're at a good sort of stopping point where we're about done with modeling and time to start with searching, and also like dinner's almost ready. So that's an even more pressing reason to take a break. But I will be back with part 2. Thanks for watching, and I'll see you next time.